Hello and welcome to week 3 of the online particle physics course. We've had quite a break in between, so let's just take stock and do a small recap of the topics that have already been covered. We have, for example, seen what symmetries are. We have seen that symmetry is anything which keeps the action invariant. For example, if you have a circle and you rotate that circle through any angle really, then the circle remains a circle. You cannot differentiate between the configuration that you started off with and the configuration you ended with. Okay, so that is the symmetry of the circle. The circle is symmetric under rotation through any angle. And with respect to symmetries, there's a very important theorem that we learned, and that is, with every continuous symmetry there is a conservation law. And what we mean by continuous symmetry? A continuous symmetry is any symmetry which you get by compounding very small symmetries, very small transformations. For example, if you rotate this circle by very small angles, no matter how small, the circle still remains a circle. So that's a continuous symmetry. That is not valid for something like a square. You cannot rotate the square by a small angle and say that that's a symmetry. You have to rotate it by 90 degrees or 180 degrees. And this is, of course, Noether's theorem. Here is MA Noether, that with every continuous symmetry there is a conservation law. So with every with a symmetry like translation through space, there is a conservation law which is called which is the conservation of linear momentum. So if you take a system and translate a little bit through space and the system remains invariant, then the quantity that is conserved is linear momentum. What about rotations? Rotations conserve something called angular momentum. And if your system is such that it does not change with time, then the quantity that is conserved is energy. We also discussed about degrees of freedom, and the degrees of freedom are basically the number of different ways in which a system can move. For example, if you have a carom coin on the table, then it's restricted to the 2D plane. Restricted to the 2D table only. It doesn't have a third dimension in which it can go. So it has two axes in which it can move. Okay. Of course, the degrees of freedom can be of two types. One is a space-time degree of freedom. And space-time degrees of freedom basically tell you how a certain object can move in space and time. And there are the internal degrees of freedom, which is basically something like spin, which an object gets purely because it exists. And spin, as you know, is a quantum mechanical degree of freedom. Okay, it is inherent to a quantum mechanical object like an electron. So if you have an electron like this, you cannot avoid spin. Okay, and as you know, the degrees of freedom are associated with different energies of a system. A spin of an electron is also associated with the energy of the electron. If you put that electron in a magnetic field, it will try to align the electron. The magnetic field will try to align the electron in the direction such that the energy of the whole system is minimized. And we had things like spin chains, where you had several spins lined up. The whole system was immersed in a magnetic field, and we saw that this system had the tendency to align in the direction of the magnetic field, because that tended to lower the energy. And the spin also helped us classify particles into spin half particles and integer spin particles. We know the spin half particles are called fermions and integer spin particles are called bosons. We saw the differences between a fermion and a boson. I hope all of this is quite clear to you. If they are not, please go back to the lectures. Please feel free to leave questions in the comment section. These are just the basics. These should be clear, otherwise we can't move forward. Let's just continue with a recap. We also heard something about antiparticles, and this is a picture that we saw. This is a photographic plate, and we have a gamma ray photon coming from this side, and the gamma ray photon suddenly decides to split itself into an electron and a positron. We know that they split into these two different particles having opposite charges, because in the magnetic field they move in two different ways. So charged particles do that. Charged particles move in two ways if they're differently charged. If this is the negative particle, this has to be the positive particle. And I told you that the experimentalists had measured the radius of the curvature, and the radius of the curvature for this event and many other events came out to be exactly the same. And because they're exactly the same, I told you the charge by mass ratio, the E by M ratio, are the same for both of these particles, but of course they're oppositely charged. They're oppositely charged and have the opposite E by M ratio. They're the same particles but with the opposite charge. So we discover a whole world of particles which have the same mass and the same spin but of opposite charge. So electrons have a partner called the positrons. The photon, of course, is its own antiparticle. Okay, but electrons have a partner called positrons. The positrons are exactly the same as electrons with respect to the mass, the spin, just that the charge is opposite. The positron is +1, the electron is -1. You can say the same thing about protons and antiprotons as well. The photon is of course its own antiparticle, which is one of the very few particles which is its own antiparticles. We also saw a problem with identical particles, the identity of particles, which basically tells you that two quantum particles cannot be differentiated. Okay, so every electron in the universe is just the same as every other electron. Okay, there are no blue electrons or red electrons. So if you have something like this, a blue electron, a red electron, okay, then that is quantum mechanically not allowed. This identical nature gives a whole new problem of counting. Okay, this gives a whole new problem of counting, because these two don't form two different configurations. For example, if you if they were really red and blue here, you could switch the positions and you would get a new configuration, but here you don't, because they're just the same, right? We discussed just briefly about fermions and bosons, and the spin determines how the particles are counted. Okay, if they're fermions, they're counted in a certain way, which is called the Fermi statistics, and if they are bosons, which are integer particles, they follow something called Bose statistics. And fermions have this very peculiar property of the Pauli exclusion principle, and I told you that fermions, no two fermions stay on the same energy level. Okay, please go and recap the Pauli exclusion principle if you don't remember. It's an extremely important principle. Told you briefly difference between fermions and bosons, except for the statistics. The fermions, they make up everything. They make up the matter that we live in. So everything that you see around you, in fact yourself, they are made up of electrons, protons, and neutrons, and those are all fermions. Okay, the bosons don't make up matter, but they play an important role in the fact that they are the force carriers of nature. Okay, so they carry the forces, like they carry the electromagnetic force from one place to another place. They carry many other forces. They carry the force of weak nuclear decay. Okay, and we'll come to weak forces plenty in the course later on. Let's continue with the recap. Last week we saw Planck's Blackbody radiation, and which was basically got by analyzing radiation coming from a blackbody. Let me just remind you what a blackbody is. A blackbody is a body in which is a perfect absorber. So once the radiation enters a blackbody, it never comes out. Okay, and we were trying to analyze the radiation. Which is coming out. So a blackbody absorbs everything. Of course, the best absorber is the best emitter. So blackbody is a perfect absorber, and so it emits radiation from its own, and it's a perfect emitter of radiation. And if you have a small hole, we can take the radiation out and we can analyze the spectrum. We studied that using something called Rayleigh-Jean's law, and this was from classical physics. And Rayleigh-Jeans basically took a lot of standing waves inside the cavity, and it led to something called the UV catastrophe. Okay, and I'll show you a graph in the middle in a moment. And this was this was the power which was derived. We can kind of motivated this. We didn't quite derive it. We kind of motivated. This was the power per unit wavelength that was derived, and we saw that the power went as lambda to the power, rather 1 by lambda to the power 4, which is extremely important. So this is the extremely important 1 by lambda to the power 4 factor. What it tells you is that if lambda is 0 or near 0, this quantity is extremely large. Of course, lambda can be very near 0 because lambda being very small corresponds to the frequency being very large, and of course you have large frequencies. So what this formula tells you is that there are many large frequency modes, and they contribute in a very dramatic way. They contribute in a way such that the power basically blows up. And in order to solve this problem, this was of course called the UV catastrophe. UV in the sense that UV is often used for very high frequency modes or very low lambda modes. Planck came in and tried to modify this formula. He came up with the hypothesis which says that okay, energy is not smooth. The energy levels are not smooth, they are discrete energy levels, and only in these discrete energy levels could energy be exchanged. And he came up with this marvelous formula, and what I want you to notice are these two factors, 1 by lambda to the power 5. So he had, instead of 1 by lambda to the power 4, he had 1 by lambda to the power 5. But apart from that, he also had this exponential factor. And if you know anything about exponents, is that if this factor is very large, okay, and if it's in the denominator, this whole factor is extremely large. So if there is a factor which is very large in the denominator, this whole thing falls down. So this is the all important factor. Okay, so let's just see what graphs we get. This is the graphs that we get. So this is the 1 by lambda to the power 4. This is lambda plotted. This is the wavelength plotted on the x-axis. This is the power plotted on the y-axis. This is what the Rayleigh-Jeans law tells you. So after a certain interval, rather if you get close enough to 0, the lambda behavior, the 1 by lambda to the power 4 behavior, make sure that this goes to infinity very soon. This just blows up. However, this second law, Planck's law gives a very nice behavior for low lambda. If lambda is low, this quantity in the bracket here, just in the bracket here, is very high because 1 by lambda is very high. So lambda is low, 1 by lambda is very high, and exponential of a very large quantity is itself a very large quantity. Okay, so for small lambda, we're getting a very large quantity in the denominator. So in the numerator, when it goes up, it gives you a very large suppression, which is a very small quantity, and therefore this goes to 0. Okay, this goes to 0 on this side because of the lambda to the power 5 dependence. So on this side you have a lambda to the power 1 by lambda to the power 5 dependence. Over there, here you have an exponential 1 by exponential dependence, and therefore this is your Planck's law. And these are the experimental points that you see, these white dots, and you can see that they fit the curve very perfectly. So we learned that energy is not transferred continuously, but they're transferred via quanta. Okay, in other words, energy is quantized. So the black body, which we thought could absorb energies any way it could, turns out that it cannot. It can only absorb or emit fixed quanta of energy. Okay, and energy is not wavy and continuous, it is rather lumpy and discrete. So energy occurs in discrete packets, and that is important. Okay, and of course after Planck's black body law, which came in the year 1900, we also saw something else. We saw Einstein's photoelectric effect, and rather the photoelectric effect and explanation by Einstein. So photoelectric effect is a simple effect. You have a certain metal, okay, which when irradiated with light gives off electrons. So that's the photoelectric effect. It's photons, okay, photon being a particle of light impinging on a metal, and that giving off electrons. Of course, people did experiments on this. There were a few observations, and many of the observations were unexplained. The one observation was that there was no time delay between the incidence of light and the ejection of electrons. So as soon as the light was irradiated on this, the electrons started to fly off. So you can this is a problem because, of course, the metal need not need to get heated. Okay, so the ejection of the electron happened because of light and not because of heat, and nobody knew how. And of course, I showed you this graph where you have increasing light intensity of one, but the light is of the same wavelength, it's of the same color. Okay, if the light is of the same color and you have the increasing light intensity, then photocurrent increased. Okay, there's the current produced, the number of electrons produced by this process increased. Okay, and if you have but very crucially, I have to point out that the stopping potential did not change. The stopping potential was the same. If you have increasing light frequency but the same intensity of light, okay, here the intensity of light was increasing, here the intensity of light is the same but the frequency of light is increasing, then the photocurrent remained the same. Okay, but the stopping frequency, the stopping potential were different. Okay, stopping voltage is different from red light, green light, and blue light, but the photocurrent is the same. Okay, and of course we saw that there is a threshold. Then there is a threshold which was there's a threshold energy, and the energy and it dependent from different metals. So if you had say for example red light shining on potassium and you had 1.77 eV of energy, potassium you need minimum of 2 eV energy, and this red light produced no electrons, but the green light did and the blue light did. Okay, and it turned out the blue light produced higher energetic electrons than the green light, and the red light did not produce anything. Okay, and Einstein's explanation came in the same spirit as Planck's explanation. He said light comes in quanta. So light comes in quanta is very similar in spirit to energy is quantized. Okay, Einstein called these quanta photons. Okay, and in that one stroke he could explain everything. The increasing intensity of light is just number of photons increasing. If the number of photons increased, obviously it would eject more electrons. If it eject large number of electrons, so the photocurrent would be very large. If the frequencies are different, then according to frequencies the light would have different energy. Okay, so in fact the energy of a photon is E equals to h nu, so depending on the frequency the energy would be different. The higher the frequency, the higher the energy. So blue has the higher frequency than red, so the energy of the photons is higher as we go, and if you have higher energy of the photons, the stopping potential will be higher. Okay, and this was explained very simply by the fact that every metal has something called a something called a work function. Okay, if you have something called a work function, then that is the minimum amount of energy you have to submit, you have to produce in order to eject an electron. Okay? If this is irradiated with anything which has less energy, then no electrons will be emitted. With exactly that energy, the electron will be emitted, but it will have zero kinetic energy. Okay, and if you impinge it with higher energy electrons, the high energy photons, the electrons which are being emitted will move out with higher and higher speed. Okay. So Einstein wrote down this very simple equation where you have the energy of light on one side and the energy of the electrons on the other side, and the conservation of energy basically tells you that they should be the same. So you have the energy of light on one side, this is the nu is the frequency of the light which is hitting the plate, and W is the work function. Okay, so this is the energy which is given by light, this is the work function of the metal, and this work function depends crucially on the metal itself. So potassium is a different work function than sodium, and so on and so forth. It does not depend on the light. Okay, and this measures the energy of the ejected electron. Okay, this is the kinetic energy. So that is all that we learned from last time. And in the next lecture, we'll see what an atom looks like and how we build that picture up. See you there.